Hello and welcome. In this video, we're going to talk about different methods for computing limits. We're going to talk about how to use different limit properties and how to evaluate limits analytically using factoring and conjugates. The second part, or the second video that comes after this, we're going to focus on using trig to analytically evaluate limits. So our goal in this lesson, I can use limit properties, and our second goal, I can evaluate limits analytically with factoring and conjugates. Let's go ahead and jump right in. All right, so we're going to talk about some properties of limits that apply when we have two separate functions that have limits that exist. So we're starting with it being given that the limit as x approaches c of f of x is some number L, and the limit as x approaches c, the same value, of g of x is m. What that means is if we're adding these two functions together and taking the limit, or subtracting these two functions and taking the limit, we can just do that addition or subtraction of the value we know that those limits are equal to. If there's a number being multiplied, so if it's 2 times f of x, we can actually just multiply that 2 after we take the limit. If we're multiplying or dividing, as long as we don't divide by 0, we can just multiply or divide those two numbers. Again, given that both of these limits exist at the same c value. And then this last one is that if we have an exponent, we can actually deal with the limit and then raise the limit to the exponent, so L to the power of n. So I want you to practice in this lesson with these three problems, actually working through and writing the limit properties as you're using them. So let's go ahead and look at this. We know that the limit as x approaches c of f of x is 2, and we know that the limit as x approaches c of g of x is 12. So if we're just dividing them, what we're going to get is 2 over 12, or 1/6. But here's what I actually want you to show. I want you to show the property being used. So we're going to say this is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x. And then we can say this is equal to 2 over 12, or 1/6. And then I'm going to actually have you rewrite the limit statement just like we did in the last lesson. F of x over g of x is equal to 1/6. Okay, number 2, this exponent to the power of 2/5, we can actually take the limit first. That's what our limit properties say. As long as this limit as x approaches c of f of x exists, which it does. Let's clean that up a little bit. There we go. So what we can do is we can evaluate the limit first, which is going to give us 2. So this is going to equal 2 to the power of 2 over 5, and 2 squared is 4. So I'm going to rewrite this as 4 to the power of 1/6. So the limit as x approaches c of f of x to the power of 2 over 5 is equal to 4 to the 1/5 power. I'm going to encourage you to pause the video and try and work through number 3 on your own. Make sure you're showing those limit steps that I've been showing in black before you substitute in the values that you know. Then unpause the video and see how you did. So hopefully you had time to work through this. Here's the step where we're applying the properties ahead of time. And now I'm going to substitute in what I know. I know this limit is 2. I'm subtracting 2 times the limit for g, which is 12. And that's going to give me 2 minus 24, negative 22. And I'm going to rewrite that final statement. The limit as x approaches c of f of x minus 2 times g of x is going to equal negative 22. Now that we have built these skills, let's go ahead and look at a different type of example. All right, so in a previous lesson, we talked about how to evaluate a limit using direct substitution. So if I had a limit statement like I do in number 1, I could just substitute 0 in for each of the x's. But if you notice, when you try to do that here, what's going to happen is you're going to get 0 over 0, and that's called indeterminate form. And there's other versions of indeterminate form, but that's the one we're going to focus on today. If we get 0 over 0, that doesn't necessarily mean that the limit doesn't exist. It means that we need to try something different. And what we're going to do is use some algebra skills that we have learned in the past to help us try something different. So one of the things that we can do when we get to indeterminate form is we can actually try to factor. So we can factor the numerator and factor the denominator, simplify to get two limit statements that are equal. The functions won't be equal, but the limits will be. And then see if we can use direct substitution. So let's go ahead and write that down. Okay. So pause the video, make sure you get those sort of steps and ideas down, and then we're going to look at example number 1. So I can't use direct substitution because I would get indeterminate form. What I notice is that in the denominator, I can factor an x out. And once I've done that, I can divide this x out. So this is going to give me not the same function. Well, it's going to be the same function everywhere, but at that one particular point when x is equal to 0. These two functions, x over x squared plus x and 1 over x plus 1, they're not equal, but their limits are equal. We just divided a factor out. Now I can use direct substitution and plug in 0, and that's just going to give me 1. So I can say the limit as x approaches 0 of x over x squared plus x is going to equal 1. So that's the first strategy that we can use. We can factor the numerator and factor the denominator and then simplify and see if we can use direct substitution. The second strategy that we can use is the conjugate. And the spoiler, the thing that helps you realize you might need to use the conjugate, is when we have a square root sign. So what you can do is multiply the numerator and the denominator by the conjugate. After you do that, you're going to have a factor that divides out, so you're not actually going to distribute the conjugate to the part that's not conjugated. I'll show you what I mean there. And then you're going to be able to hopefully use direct substitution. So pause the video so you can take that down, and then we're going to go ahead and jump into number 4 here. So I'm going to multiply by the conjugate. So the very first thing, and I didn't say this, but I'm going to say it now, the very first thing I should always do is check to make sure I can't just plug in the number. Direct substitution is always going to be easier, but that's going to give me indeterminate form. So now I'm going to multiply the numerator and the denominator by the square root of x plus 1. So conjugate meaning these two things are exactly the same except the sign is different. The reason we multiply by the conjugate is because what's going to happen in our numerator here is we're going to get the difference of squares, which is going to be x minus 1. The square root of x times the square root of x is x. The plus and minus root x are going to add to be 0, and the plus and minus 1 are going to give us our minus 1. In the denominator, this is where I'm going to have you not actually distribute. So there was already an x minus 1 in the denominator, and we're multiplying that by the square root of x plus 1. So notice now we have a factor that divides out, which means now we can use direct substitution. We're going to have 1 in the numerator, and in the denominator, we're going to have the square root of 1, which is 1, plus 1, which is 2. So the limit as x approaches 1 of the square root of x minus 1 over x minus 1 is going to be equal to 1/2. So let's look at a few more examples. Here we go, last 4 examples of the video. I'm going to encourage you to pause the video, factor if it looks like it's going to factor, use the conjugates if it looks like it's going to need to use the conjugates, because none of these problems are going to work with direct substitution, so we're going to need to use a different strategy. If you're stuck on factoring on number 6, I'm going to walk you through that one specifically in just a minute. But pause the video, see how far you can get on these 3, and then unpause the video and see how you did. All right, so go ahead and check over your answers to 2, 3, and 5, making sure that you factored correctly, that your notation looks good, that you have a limit there until you no longer have an x. And then let's talk about number 6. On number 6, you have to be able to factor a perfect cube. So just a reminder on how to do that here. So if I'm factoring the numerator here, I'm going to get the limit as x approaches 1. The cube root of x is x. The cube root of x cubed is x minus 1, and then we're going to change the sign to be positive, and the last sign is always positive. I learned a little acronym called SOAP to help me remember this is going to be the same as the problem, this is going to be opposite the problem, and this is always going to be positive. Now that factor is going to divide out, and that's going to give us the limit as x approaches 1 of x squared plus x plus 1, which allows us to do direct substitution and get 3. So the limit as x approaches 1 of x cubed minus 1 over x minus 1 is equal to 3. If for some reason you could not remember how to do factoring of perfect cubes, you could always divide x cubed minus 1 over x minus 1 and get to the simplified form in that way. So let's go ahead and wrap up this video. Our goal in this video was to learn how to use limit properties and to be able to evaluate limits that result in indeterminate form analytically using factoring and conjugates. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.